All right, so let's pick up here with our program counter related to ARM. Or in your reading, you maybe have seen there's a kind of a lightweight version of ARM called Thumb. Kind of funny, you know, you have your whole arm versus you have your thumb, but in any case, ARM handles program counters a little bit differently than other architectures. So the program counter, if we were just generically going to say, what does it do? It is, it holds the line number of the next instruction to execute. That's what the program counter does. So when we say instruction to execute, that's the next instruction that's going to get loaded onto the CPU. Historically, other architectures literally hold what I just said. They hold the number of the next line that gets executed, whereas ARM actually holds 2 lines ahead. This is for an optimization technique, especially with multi-core processors, to allow it to more quickly get to the next processors, knowing it's always 2 offsets off of where the next instruction is. So we have the next, and the next. So we have all 3 instructions, I guess, more conveniently available. I don't take that for what it is. You know, they consider it to be an optimization. I'm not sure it's that big of a deal, but that's the reason that they do it. All right, so some examples. Last time we talked about loads and stores. So some examples here is we might load into a register R0. Remember this from last time. We have the anything inside of these square brackets is get the value at. So this says go to memory address, whatever PC currently holds, and then take, this is 12 byte size steps, where each instruction is 4 bytes. So this would be take 3 instruction size steps. So if an instruction is 4 bytes big, 32 bits, we would start off at whatever address the program counter currently says, and we would take 3 instruction steps forward in this line of code. So we're saying, give us the value that lives there and load that into R0. Give us the value that lives here and load it into R1. From R2, load whatever's in R0. And then we're going to store whatever's in R2 into the memory, the address of R1. So R1 holds the memory address. We're going to actually go to real system memory and store the R2 there. Okay, so that's just kind of some examples of how the program counter might work when we're bringing values into, we're loading something from memory into a register. It's kind of a special use of program counter in ARM. All right, so this operates off of, we just saw it there, this idea of a memory offset. And you know, in older classes, we've probably talked about arrays at some point. You've had some teacher or me talk about arrays, where arrays hold a base address. They require a bunch of contiguous memory. So if you want to hold 10 integers, for example, in an array, and an integer is 32 bits, you would need 320 bits of total memory, or 40 bytes of total memory to hold 10 integers. Now, not only do you have that in total memory, that memory must be right next to each other, because of the way arrays work, similarly the way a lot of our architecture stuff works under the hood, is you go to the starting point, the base address of a place in memory. And then if you want to get to like bucket 7 of that array in memory, you will take 7, in our example here, 7 integer size steps through memory from a starting point to get to the actual place in memory. And that's not dissimilar to what's happening right here. This says we're going to put some value in R0. What value are we going to put there? Well, we're going to start off with wherever the program counter is. And then we're going to take 12 bite-sized steps from there to get to a new place in memory that's, relatively close to this guy, but a little bit farther down the road. And it's that value, the value we find there, that we're going to load into R0. All right, so this idea of base addresses and offsets, this is something we find in our high-level programming languages. It's something we find underneath the hood in our assembly language. Is how computers typically work. Okay. So we ask, why do we do this? And this comes down to an example I've used earlier where I say, think about your computer memory being like one big long street, where, if you have 1 million people living on the street, you have house 0, house 1, house 2, house 3, so on and so forth. Give me 1 second here. My wife wanted me to do a quick experiment. She keeps hearing me yawn in the morning, so she told me she wants me to take my blood oxygen level. So I'm just following the rules. All right. Oh, I passed with flying colors, 97. Oh, that's better than it usually is. All right. So in any case, we talked about memory being this one big, long street. And the reason, so we kind of asked the global question, why do we put stuff in memory versus read it directly off the hard drive? Well, we've already had the discussion. It was 97. Okay. We've already had the discussion that the closer you get to the processor, typically the smaller but faster the memory tends to be. So hardware registers are faster than L3 cache or L1 cache, which is faster than L2, which is faster than L3, which is faster than the system memory, which is faster than the hard drive. So really our slowest type of memory in our computer is our hard drive. Okay, well, so if we want our, and we might say that the processor in our computer is super fast, right? Well, so if our processor is this greedy thing that wants to, be fed instructions really fast, it wants to eat those instructions off of a fairly fast source. And system memory is going to be a much faster source than your hard drive is going to be. Okay, so what's the punchline? The punchline is we need to get stuff from our hard drive into system memory. That has to happen. All right, so when we're talking about loading instructions from assembly, we're feeding off of system memory, moving things into, moving things onto the processor, and that comes in the form of loading things into registers like this. So when we have something over here, what we're talking about is retrieving something from system memory. All right, and again, whenever we see the square brackets, and I happen to like this about ARM assembly, is the square brackets really do remind us of arrays. So this says go to some bucket in memory, and that bucket is the memory address of this guy plus this guy, and that's going to take us to a location, and then the square brackets here say give me the value that you found at that location. And that's exactly how arrays work in high-level languages. So I like when we have consistencies like that. If it works in Java or C#, why can't it work at an assembly language? As opposed to some older assembly languages, they'll have you load the offset into one register, and they'll have you load the program counter into another one, and then you got to do some math with it, and then you got to retrieve the value. It's a more complicated thing that ultimately accomplishes the same thing. So one thing we do see in ARM, and really it's a tenet of RISC processors, reduced instruction set processors, like ARM is we kind of see these instructions that kind of have built-in like combo moves. They do a little bit more than the super granular stuff that might happen in a different architecture, with the emphasis on, hey, these are things that you commonly are going to want to do. So since you're going to commonly want to do these 4 instructions in a row, why don't we just build them into a single instruction for you? Something along those lines. All right, but at the end of the day, we want to be feeding off of system memory, so we have things built into assembly specifically for walking system memory. That's an important part of working with any kind of computer hardware. Okay, and like we said, just going through the text here, system memory is relatively fast compared to hard drives. It's also relatively large compared to our registers and cache. Your computer, this computer I'm on right now, has 16 gigabytes of system memory. And if you remember when we looked at the various mobile processors, I think they maybe would have had like 1 megabyte of L3 cache or something like that. And a hardware register we've been looking at is like 32 bits or 16 bits or 8 bits. So way smaller. So we need to be a lot more careful about how we use our bit space when we're messing around with the registers. But hey, when you got 16 gigabytes of RAM, or my other laptop has 64 gigabytes of RAM in it, you got plenty of room to kind of stretch out, so you can load, and this kind of comes down to, where do those instructions that end up in memory come from? And well, when you double click on your icon on your desktop or whatever, it's going to load your computer program, Microsoft Word, whatever it is. It's going to load it from your hard drive into system memory. Okay, maybe it loads it in part, maybe it loads the entire thing, but at the very least, it loads enough of that program into system memory to get the ball rolling. So one thing they say is, if your computer doesn't have a lot of memory in it, and when they say not a lot of memory, they're talking about system memory, you're kind of limited in the number of applications that you can run at once, because it's going to be trying to load all those applications into system memory at once for every application that you open. Our modern operating systems have some hacks for hopefully helping you work with that stuff. They have something called virtual memory, where it treats part of your hard drive as system memory. So, just because you're treating it like system memory doesn't mean it's as fast as system memory. It's going to only be as fast as a hard drive is. We've improved our state of things a little bit more recently with our solid state hard drives. I don't remember if we talked about that, but let me actually bring up a thing, because it's a pretty fascinating comparison. Something's going to kind of give us it in chart form. That chart up there is not actually, I bet you maybe under images we'll find a direct comparison. Okay, so and these things might even be a little bit dated, but this just gives you an idea. So our historical hard drives, so whenever you're buying a computer, if it says HDD on it, which still does exist today. Sometimes if you're buying a gaming computer, you'll have some solid state drive in there, and then they'll put like a 3 terabyte mechanical drive in there for like holding your games, because the video games have require large amounts of storage, and because hard drives have been around longer, from a cost-effective perspective, you can get huge amounts of storage in a mechanical hard drive versus solid state drives, where the price starts becoming more expensive as you get to a larger drive, although solid state drives have dropped way in price. So now, I mean, you can get a 1 terabyte drive for not that much. A 2 terabyte drive is actually pretty reasonable now, where that used to be pretty prohibitively expensive. I would say there was a long period of time where like a 512 gigabyte solid state drive was kind of the cutoff point. Anything bigger than that started becoming 3 or 4 times more expensive. But now they're very affordable. But when we really talk about the performance of solid state versus hard drives, so in our discussion right now, we're talking about hard drive versus system memory versus cache versus hardware registers. In your computer, if you have a solid state hard drive and you're feeding off of that, loading stuff into memory, versus a mechanical hard drive, HDD, whose speed is based on number of RPMs, because it's literally spinning. So typically these are going to be 7,200 RPM hard drives. If you get into the higher performance ones made for servers and things like that, you can get 10,000 or 15,000 RPM drives, and they typically have heat sinks and stuff in them because that's going to start getting hot. But even with that, they're still way slower than solid state. So kind of starting off at this top point here for access time, so how long does it go and take to look something up on the hard drive? Just like we're talking about finding an offset in system memory and going to bucket 30, system memory is fast. It's really fast. It's going to be faster than this. Okay, but look at how much faster a solid state drive is at 0.1 millisecond to access someplace on the hard drive versus 5.5 to 8 milliseconds. That's hugely faster. This is effectively instantaneous versus a wait. So random IO performance, or reading stuff from the drive, not just accessing it, but reading it. 6,000 IO instructions per second. So we can ask for 6,000 things per second versus 400 things. Again, not even close. Reliability, solid state drives are more reliable, although, I mean, really this hard drive thing, 2 to 5%, that's probably, a somewhat of a misrepresented number. All of our hard drives these days are reliable. Where it would become problematic with a hard drive was in like laptops, where there was a lot of jumbling around and stuff like that. Like, with me, I have my laptop and I might just shut the lid. It might be doing something, and I might just shut the lid, throw it back in my backpack, wherever, and go. So it's jostling around back there and stuff like that. Well, with a solid state drive, there's no moving parts. So who cares? It jostling around and stuff isn't a problem. If you have this spinning drive back there, you're bouncing it around, you got physics acting on it and things like that, that can start becoming a problem. And so we started building kind of protection mechanisms into our hard drives. But I would say the failure rate for a mechanical hard drive is not very high when you're talking about like desktop computers. Laptops is where it gets a little bit more sketch. Okay, but we're still saying solid state drives are more reliable. Energy savings. So solid state drives between 2 and 5 watts versus 6 and 15 watts. So they use less electricity. So in terms of the amount of CPU power it takes to work with that drive, I'm not sure how measurable this really is, but they're saying it only takes 1% of your CPU to manage a solid state drive versus 7% for a hard drive. And part of that probably comes down to the IO things, reading stuff in and out from the hard drive, because you have to delay. The processor is going through a lot of context switches, where we're having to move, while one application's in the process of moving into memory, we have to move on to another process, and that takes time to get one process off the CPU and another process loaded onto the CPU. So all those little delays kind of add up to less efficiently using our processor. Input output request times. So again, IO is expensive. You know, we've seen that in computer programs before, and you know, and we can see it here. Let me just show you real quick here. So I'll just do a vi test.java. Well, let's say we just want to have a computer program that's going to count. So for int I is equal to 0, I is less than, say, 1,000,000, I plus plus. Let's go to 10 million. We'll exaggerate it. Oop. And if all we're going to do in here is say count plus plus, and then in the end, after we've done all the counting, we'll print out our count once. Something like that, where we're going to loop through and just increment count 10 million times, and then print out one time. If I go ahead and run this, you see how quickly that ran. Basically, from our perspective, instantaneously. If I just make one little change here, and instead I print out count every single time I've incremented it, which doesn't seem like that big of a deal. All of a sudden we have a program that takes a very long time to run. And it's because IO is expensive. All those little system.out.printlns, when we're printing something to the screen, that takes time. And every single time we had to do that, our process had to leave the CPU, come back onto the CPU. So even though that didn't seem like a ridiculous amount of time there, it was horrifically processor inefficient. Because our process had to keep leaving the CPU so that it could work with the operating system to display something on the screen, just to get back onto the CPU to add one to count to only leave the CPU again. Something along those lines. So definitely problematic. All right, so IO is expensive anyways, but we see that if you're doing IO with the solid state drive, it's about a 20 millisecond access time, request time, versus a solid state drive or a normal hard drive, 400 to 500 milliseconds. So solid state drives also move data quicker, so they back up more quickly, yada, yada, yada. So when you really look at these two, there isn't one category where a traditional hard drive even comes close. And so it's not even a slightly better situation. Solid state drives are orders of magnitude faster than hard drives. So when people are trying to speed up their computers, if you have enough system memory, the next place to look is replace your mechanical hard drive with a solid state drive. You'll notice a instantaneous jump in speed, and you'll feel that speed because every single time you click on a program, it's having to load that program from your hard drive into system memory. And if your hard drive can feed that stuff to system memory fast, you're going to benefit from that in terms of how you feel. Okay. And all of our mobile devices are based on solid state technology for the reason I mentioned a few minutes ago, where, you know, historically a laptop might have a mechanical hard drive in it. And well, that can become problematic since laptops are constantly being bounced around and things like that. And you maybe have even seen it before when you were shopping for a laptop or something, where you'd be on a website and they'd be selling a 1 terabyte hard drive for the laptop, or you could upgrade for like $300 or something, to a 512 gigabyte hard drive. Like, okay, well, my storage is cut in half, yet they're calling it an upgrade and they're charging me more money. To an average consumer, that's not going to make a lot of sense. But to us, we understand that under the hood, we're dealing with a faster piece of equipment. Sure, it holds less data, but our access to that data is orders of magnitude faster. Not even close. We're not talking. We're talking about I don't know, like a Ferrari versus like me on foot, something like that. And I'm quite quick. I'm agile. So in any case, something to keep in mind with just the speed of our various hardware things. Farther we get from the CPU, the slower and larger memory tends to get. But when you get even to that hard drive area, the technology of the hard drive really does make a big difference. All right. And at the end of the day, whenever we double click on an application to load it, it has to load the bytes associated with that application into system memory. So system memory is always relatively fast compared to your hard drive, but now we have performance memory, faster megahertz, gigahertz, whatever memory, DDR3, DDR4, these different memory technologies that are coming out that make the memory access times faster and faster and faster and faster. But still, I don't think you're going to see the leap in performance difference than we just saw with the solid state versus traditional hard drives. You're going to see, percentage increases between last year's, latest, greatest memory technology and this year's latest, greatest memory technology. All right. But all of our mobile devices today use solid state drives for multiple reasons. Obviously, we just saw from the chart, they're faster in every single way. They're better in every single way. Literally every single way. There's nothing about a hard drive that is better than a solid state drive. Maybe if maximum storage capacity was your only concern, maybe you can then argue that a traditional hard drive will give you more storage, but even that's becoming less true as our solid state drives are becoming very large as well. Okay, and we've already talked about this, but just for the use of our registers, what stuff actually gets loaded into these registers? Well, it's the stuff that the CPU is going to need next. All right, the CPU, when it's eating its instructions, it's executing its instructions, it's going to be utilizing the values directly accessible to it that are sitting in the hardware registers. That's why we load things into those hardware registers so that they're ready to be used by the CPU, because that's where it's the fastest. And we want to maximize our CPU's efficiency. If we need a little bit more storage space, but we still want it to be pretty fast, that's when we can branch out into like the L1, L2, L3 cache. So these are larger chunks of memory that sit somewhere between the hardware registers and system memory. And these guys allow us to store more data, but in a kind of a grab and go way. It's more readily available to us at a faster speed. L1 and L2 cache is shared by is used by a single core of a processor, where L3 is shared between cores of a processor. So it can be used for interprocessor communication when we have processes running on different processors. All right, we've done some of this math stuff before for the size of the registers, how many registers would we need to hold 2 terabytes. But really the argument for this slide is that reiterating that the closer you get to the CPU, the smaller and faster the memory is. So if we were to say a 32-bit register costs $1, this is just kind of a money comparison. So let's just make the assumption that a single 32-bit register on a processor costs $1. Well, if we wanted to hold 2 terabytes of data, which is not a unforeseen size, you can get solid state drives for 2 terabyte solid state drives for $150, something like that. Not ridiculous. How much would that cost if we were using the hardware register technology? Well, it would cost $549,755,813,888. We're probably not going to spend that for a 2 terabyte hard drive made of hardware registers. It's just not cost effective, obviously. So we see that the cost difference between the per byte cost of a hardware register versus a other types of storage. Okay, and we're already starting to see some of this stuff, and specifically with mobile computers. We have to start expanding our definition of what architecture really means. Historically, we would say architecture is the actual design of the hardware, but then you think about, you have some of you, I know I've talked to some of you, you've actually worked in these positions before. You've been something called a system architect. And system architects, that's more of an IT position. And it typically is somebody who is solving a problem for a company where you're bringing together multiple different technologies with an ultimate goal of having them all work together. And each one of those technologies is running on maybe a different computer, running different hardware with a different size, system memory or hard drives, yada, yada, yada. Okay, but our definition of architecture becomes broader because of the things that are at play. Similarly today, when you go out and buy a new smartphone, you can buy a smartphone in I don't know where the smallest is anymore. Maybe you can still get one at 64 gigabytes of storage. Let's just assume that's the case. So you go out and get a new smartphone, you can get one with 64 gigabytes of storage versus 128 versus 256. There are 512 ones. There are terabyte ones now, but probably 256 to 512 are your larger capacity smartphones today. So when you're talking about getting a device that has 256 gigabytes of storage, what are we talking about? Which of our memories are we talking about that 256 being? Okay, it's not your hardware registers. It's not your caches. It's not L1, L2, L3 cache. It's not system memory. It's talking about your hard drive space, the amount of long-term storage that you have local on the device. So what do we actually use our long-term storage for on our smartphones? Well, it depends on your use case specifically, but we can narrow it down to just a couple of things. For those of you who take lots of pictures, you're going to use your local storage for those pictures to have quick access to these images that you've taken, even though they're often then duplicated into the cloud somewhere. We'll talk more about that in a second, for backup. Some of you might listen to a lot of music, so you might use that 256 gigabytes of storage for music, maybe video, things like that. Maybe it's apps from the App Store. You download a lot of apps, or you play these larger games that have bigger footprints. So maybe a little calculator doesn't take up that much space, but if you're playing one of these highly graphical intensive games, well, it's going to take up more space in your device. So if you're making the decision, do I get more storage, that 256 gigs or the 524, or the 512 or the 128, those things, they ultimately translate into how much stuff can I long-term store locally on this device. And that's becoming less and less relevant because we start thinking about putting things in the cloud more and more and more. Okay, and cloud computing is even involved. So historically, when we talk about storing something in the cloud, our devices, I'm on a Samsung Galaxy Fold. So my device, backs up onto the Samsung cloud. My wife's on an iPhone. I used to be on an iPhone, and it backs up onto Apple's cloud. So that when you get a new device, you just have to put the, restore from your cloud backup of your device. And, then you say, okay, well, I have 4,000 apps on my phone. Well, it's not going to back up the apps. What it does is it doesn't back up the physical storage of the apps. It backs up the fact that you have that app, and then it'll just go and re-download it off the App Store. So that way the app is only actually stored in the cloud once, and that's on the App Store. All right, but when we have storage outside of the device, that means we likely will need less storage locally on the device. Same thing, if we have compute power outside of the device, and this is actually something that has changed some over the years that maybe you've experienced. So for those of you who use any of the smart stuff like Siri or anything like that, many years ago, when you would Siri would not work if you didn't have a decent internet connection currently. Because what it would do is it would record what you said, it would send it to the cloud to compute that, and then it would send you the result back. So if you had a broken internet connection, it wouldn't be able to do that communication. Where now, at least portions of those things, and especially with voice dictation, where you're not actually asking it to do something smart, like doing Google searches or solve some problem for you, you're just asking it to turn what you say into written text. Those things have now moved on to the devices themselves because the processors have gotten faster, the battery life has gotten faster. So using that extra electricity to do that kind of stuff is less of a big deal. But historically, those were all handled with cloud computing. So when we think about cloud computing, we're talking about storage. We're talking about using processors that live in the cloud, effectively leaning on a computer that isn't the one we're on. I'm sitting here on this small smartphone, and somewhere up there's some giant array of supercomputer type things that give me a whole lot more storage, a whole lot more horsepower for crunching numbers and things like that I can leverage through my device. And we're seeing this in other examples as well. Yeah, so we're talking about the role of the internet connection. So here, I'm gonna stand for a few minutes. All right, so before I make our transition towards VR type stuff, which is still mobile, are there any questions about any of the things we've talked about today? With our current emphasis really being on what's the right storage and compute power for the job. Where do I store the next byte of data? Is it in a register? Is it in cache? Is it in hard drive? Is it in system memory? Is it in the cloud? How quickly do we need it, right? And you might imagine if you have something stored in the cloud, you will be able to access that slower than if you had it stored in your local hard drive. And that would be slower than it was stored in system memory, yada, yada, yada. So these are all relative things. Now, if we had rolled back, historically, where we had like dial-up modems, we talked about that some earlier in the course. And we definitely talked about it in the networking course for those of you who were in that last term. Our internet connections have very much become part of our data transmission protocol. Historically, they weren't fast enough, they weren't reliable enough for us to expect data to be available in real time. Well, now we have all sorts of interesting things. Let me bring something up here. Yeah, so we have like this device here. This is Valve's Steam Deck. Let's just see if we get a bigger picture of it when I go here. Yeah, this works. All right. Anybody know how the Steam Deck works? Anybody in here have a Steam Deck? All right, so if you're a PC gamer, let's say, you have a common place where you might have a lot of your games is on something called Steam. So Steam is kind of a game catalog. They're not the ones necessarily making the games. They're just distributing and charging people for games and then keeping them in a kind of a cloud storage type thing for you. So if I've bought 20 games on Steam and I have 3 computers, I can load Steam in those 3 computers and download those games locally conveniently using Steam. So it's a game management tool. Well, up to this point, and this is really becoming, if when somebody says, oh, I play computer games, the first question for anybody who's a gamer, the first question they might ask is console or PC. Okay, because there's 2 different breeds of gamers. Console gamers, these are people that are going to be using like a PS4, PS5, if you can get a PS5, or the Xbox, the Xbox latest greatest, or the previous one. It's easier to get the latest Xbox than it is to get the latest PS5, but it's still difficult. Okay, but console gamers, and even that's changed a little bit, because one of the main things that, when we talk about esports initially was kind of born on console, and part of the reason why that worked is because if you had a PlayStation 4, let's say, everybody's PlayStation 4 was the same speed. You had the same processors in it, things like that. Now, after it had been out for a while, they had some smaller form factors where it was a little bit more convenient to maybe store, carry around, that kind of stuff. And that's just because of manufacturing improvements or heat dissipation improvements, but they still had the same processors in them. So literally everybody who was playing the game was playing on an equal piece of equipment. And at the professional level of esports for PCs, they do the same thing. When if you've ever seen esports like in an arena, let's see. See if I get an image of yeah, so here's like, some esports competition, all exciting. So these people are all playing a video game. These are on PCs, I'm presuming. Let's just pretend these are PCs. They probably are, based on the setup and the fact that I'm seeing monitors there, and yada, yada, yada. Although console would use monitors too. But let's assume these guys are on PC. They're all sitting in front of the same computers. Just 20 different computers with the exact same specs, same amount of memory, same processors, same hard drives, so they're all playing from the same physical pieces of equipment with the same performance. That equals the playing field. Similarly, and this is going to go back to our internet connection stuff. So if you're playing console-based video games, the hardware is relatively synchronized, although that's become a little bit less true these days. Like they had a PS4 Pro, they have a couple different models of the PS5, or one is a little bit beefier than the other one. So you kind of have like the standard edition and the Pro edition of consoles now. So you have 2 different configurations, which can add a little bit of a twist in there. But largely it's let's say it's mostly equivalent, where if you're playing a PC video game and you're online with playing just random online stuff, I mean, you have no idea where your computer sits relative to other people's computers, right? Because you're dealing with you might have somebody who is on a budget and they've built the best gaming computer they can afford, and maybe they have to have some of their graphics turned down and things like that. And so maybe with some of the graphics turned off, that makes their ability to play the game a little bit diminished. They're not seeing all the shadows that somebody else might see. They're not seeing as many frames every single second, so they can't necessarily react as quickly, things like that. They might be at a disadvantage. Or if you have somebody else who, you know, they've dedicated their life to PC gaming and they rather have a top end computer than a car. You might have somebody who's built a, you know, monster of a computer that's multiple times better than what you have, where they can play every single game with all the graphics maxed out and all those things. So we have a much larger dispersion of hardware available for PC gaming. Here I can show you kind of a fun picture, first world problem that just happened the other day. Let's see. I think I'd mentioned to you guys before, I run a VR think tank. I have a grant with Meta now. It was Facebook doing research and development for virtual reality. And I've invited you to talk to Blade or talk to me if you want to try out the VR headsets. But yeah, so this was my first world problem from last weekend. For gaming, I'm that second guy. So who you know, has ridiculous hardware capacity in their computers. So I have a couple different gaming machines at home, but so this these are graphics cards, what we're looking at here. So this graphics card that's in here right now is an NVIDIA 3080 Ti, which let's just say was the fastest graphics card 2 weeks ago. There's a 3092, but most performance tests, it was pretty similar to a 3080 Ti. This guy is the 3090 Ti. He's the new kid on the block. So I grabbed one of those and he doesn't physically fit in my case. So I can't even plug them into my computer. The card is so large. So I had to get another case and we did this whole hack thing, whatever. But, you know, kind of a funny first world problem that, you know, we often don't think about. You're like, oh, I'm going to buy more power. I'm going to get this, that, and the next thing. You know, and this stuff doesn't fit. You know, and you're just kind of looking at the stuff, you know, in this computer since we're here. You know, this is my processor here. I have some liquid cooling on my processor. This is my system memory. It's a 64 gigabytes of memory. So each of these is a 16 gigabyte chip. This processor here is a Ryzen 8050 from AMD. This is a 48 core processor, so a pretty ridiculous machine, but this is the same stuff we've been talking about. This guy has hardware registers on it, and it's going to have L1, L2, L3 cache to talk between those multiple cores. You know, this guy gives off a lot of heat. He gives off so much heat that instead of a traditional heat sink on top of this, I have a liquid cooling system. So these tubes here are moving liquid across this these tubes across the processor, which are absorbing heat and then moving it, then pumping it away from the processor to cool down, rather than just blowing hot air up into the thing. So we're seeing technology here that dissipates that heat. But the fun thing in this picture is just how giant the new graphics cards are. I mean, it's becoming obscene. That's like not even right, because this guy is considered a large graphics card. You see this rail here? Okay. That is a support structure in here to keep this card from breaking my motherboard. So this card is considered huge. So much so that it comes with a steel support structure to hold it in place. It's really becoming kind of funny at the PC gaming level of things. Just kind of a fun thing to think about at the crazy PC gamer world. And realistically, I actually don't play tons of normal PC games. I'm big into virtual reality. I don't have the reflexes anymore to play PC games at any sort of competitive level, which is fine. It's a young man's sport. But in any case, when we're looking at these esports competitions, they're having an equal playing field by having everybody on the same hardware. Okay, because just like we've been talking about, performance is based on the number of cores, the speed of your core, hardware register speed, system memory, all this stuff. And if you increase the speed of any one of those things, like we looked at the solid state drives, if one of these computers had a solid state drive in it and all the other ones had normal hard drives in it, the person with a solid state drive has an advantage. There's going to be less hiccups in their game, because when stuff is getting loaded into system memory, it's going to happen orders of magnitude faster. We saw the numbers. It's not even close. It's not even close to close. That's how much faster solid state drives are. So if you have a computer at home that's still running a traditional hard drive and you want to make it feel a lot faster, go out and spend, you can get solid state drives for like $60 now, that are like, 256 or even 512 gigabytes. So go get a solid state drive and at least put your operating system on there, and you'll notice your computer's way faster. All right. So, role of our internet connection has become more and more important in our modern day computer architecture, because now our architecture is spread between what's locally on our devices and then what's in the cloud. And the thing that links us between our local device and the cloud is our internet connection. We don't have that physical cable inside of our computer that's linking those guys together, or we don't have all those wires on the motherboard that's linking the processor to the system memory. Those things don't exist when we're dealing with cloud storage or cloud computing. So we're very, very, very reliant on our internet connections for that. All right, what I'm going to do is I'm just going to introduce this here. You already have your homework for next week looking at the Oculus Quest versus the Quest 2. So we're starting to talk about virtual reality, but let me at least give a kind of a starting point here for a couple of minutes, and then we'll call it quits. So, and I really want to focus, and that first thing was the assignment was Quest versus Quest 2. Both of these are standalone virtual reality headsets. They're not reliant on a gaming computer, because the focus in this course is mobile computing. All right, so a Quest 2 and a Quest, these are, what you really should do is you should think about it as, this is a smartphone whose screen has been wrapped in this device that has two different lenses, that when you hold it up to your face, it draws stuff on one lens, it draws stuff on the other lens, and that gives me a virtual view as if I'm in 3D space. All right, so virtual reality is a perception, I guess a perception trick. And I think I'd asked this question earlier in the course, how many of you have tried VR before? And I think it was a pretty low number of people had actually tried VR. I really, really, really recommend at some point, just from an academics perspective, go and try virtual reality. Like, we have it in the department. It's not going to cost you a dime. When you come up for one of our events or something like that, set up with me or Blade to come in and try it out. I think you will be shocked at the current state of virtual reality. And it's not just about games. In fact, part of my think tank is about how VR is good for more than games. The only reason VR seems to be focused, or has seemingly historically been focused on games, is because the amount of hardware it takes to push virtual reality at the highest level is those graphics cards like I have that don't fit inside the computer. So who has those machines with the crazy high-end graphics cards? It's the gamers. Okay, so the only people who had computers that could drive virtual reality initially were the PC gamers. So what content are they looking for? They're looking for games. So that's why games became this kind of prevalent thing in VR, even though at that exact same time, other things were coming up through there. I mean, like as an example, we have our think tank meeting each week in this is what our meeting might look like. So several of us are attending via VR. So we're in different places in the world. We have our avatars that are in here and we're talking to each other. You can see who we're looking at. You can see hand gestures, all these things. And then if there's folks who are on the road or don't have access to their headset right now, they can join kind of like Zoom. So we got just the picture boxes here. But we are in a virtual boardroom having our meetings. You can share computer screens, all that stuff. So this isn't a video game. This is a meeting. This is work related stuff, productivity related stuff. There's so much stuff in VR that's amazing. Google Maps. I've had students, especially our international students, who I'll say, "Oh, well, why don't you show me where you're from?" And you know, we put them into Google Earth, is what it is Google Earth, and I have them fly me to what part of the world they're from. And then we can zoom in, we can get down to street view and walk around. They say, "Oh, you know, I eat there. This is a good restaurant." And stuff. And you're doing that all from VR from the middle of Wisconsin. It's really kind of just an amazing technology. I think so many people discount right now just because it's not, you know, it's not prevalent in everybody's hands, but it's becoming more and more prevalent now because of mobile VR. All right, so you know, we have this device called the Quest 2. Let's see here. Yeah, so you guys are going to be looking into these guys in your paper. So the guy here on the right is an Oculus Quest 2. Oculus is owned by Facebook, which changed their name to Meta. So now this is called the Meta Quest 2. But anybody who's been in VR for a while is still going to call this the Oculus Quest. Oculus is one of the founding fathers of VR. Facebook bought them. I don't know why they're changing the name. I think it's more of a political thing because Facebook can sometimes leave a bad taste in people's mouths. So if they don't have to use the word Facebook, that's good. That's why they changed their name to Meta, but I'm not sure how Oculus hurt that, but whatever. So in any case, this is a Quest 2, this is a Quest 1. You're comparing and contrasting these two guys in your paper, but just at the high level thing here, both of these devices are standalone mobile virtual reality headsets. They do not require a computer. Right? These guys have their own processor in them. They have their own memory. They have their own storage. They have their own graphics card. You know, they are, you know, the applications they might run are reliant on, you know, less hardware. So even though you might have, for example, some games that are available both on the Quest as well as PC VR, maybe the Quest version of the game has certain aspects kind of disabled or dithered. You know, less shadows, maybe, you know, lower resolution textures, things like that. It's not bad, but it's noticeable, you know, so there is a different level between the two. But I would say for a large percentage of applications, the Quest and the Quest 2 are great devices. My daily VR headset is my Quest 2. I have an 8K Pimax headset downstairs that if I decide to travel downstairs, I'll use that. That's PC VR only. If I'm ever doing a PC VR, if I'm ever doing a VR game, chances are I'm doing it using PC VR, but I'm probably still using the Quest 2 for it. That's where these devices become very interesting, because even though this is a standalone device that does not require a computer, you can use this with a computer to use it as a PC VR headset. Now, originally that was through a link cable where you would plug this guy into your computer, but now you can do it entirely wirelessly. So I sit in my living room here playing PC VR using my Quest 2 wirelessly. So I'm not tethered. I'm not even sitting in the same room as the computer. I'm somewhere else in the house. So these things are becoming more and more impressive using these concepts of cloud computing. Role of the internet connection, so in this case, it's the role of my local wireless network in my house for streaming from that computer downstairs to the headset here in the living room. But this is related to the question I asked earlier about the Steam Deck. So nobody said that they have a Steam Deck, but the idea here is this is a video game system, not unlike like a Nintendo Switch, for example. It looks a lot like the Nintendo Switch, where it's a handheld kind of device. You could certainly plug it in and use it on your computer. But the difference here is that the Steam Deck streams games. You can store stuff locally on it, but it streams games from your Steam library in your house. So if I had a Steam Deck, I could be sitting in my living room launching computer games from my Steam library down in the basement, playing on this device, but those games don't live on this device. They are being completely rendered and run on my device downstairs using my giant graphics card and then streamed to this device that's in my hands using this network in my house. So the architecture of that video gaming relies on a computer living in one place, my compute power living in one place that's separate from the device that's actually in my hands. And then the result of the computations that are happening on the CPU and that are happening on the graphics card are being delivered to me over this network. All right. So really kind of fascinating stuff that we're seeing with these types of things, where we are moving more and more of our architecture off the devices, which really is a step back in time. Let's just do a search for dummy terminal. This is one of them. Kind of get the picture there. So this is obviously a much older machine, but this is a computer that actually doesn't have any computing power. It's a monitor and it's a keyboard, but it's connected to a network, and that network somewhere on that network is the actual computer that's providing all the processing power and things like that. That this guy is a view into that computer, but the actual computations and things like that are happening on that central computer. So this is just a dumb terminal that's only there for my input and its output to the computer monitor. All the thinking, all the processing happens someplace else. By today's standards, we might say it happens in the cloud, or in my case with the VR stuff, it happens, in a computer in another room in my house. But what's in front of me doesn't have to have all that bulk. You notice that we don't have that tower thing sitting here. You're not seeing a big tower that has your processor and your RAM and all this stuff. This guy is meant to be an external entity to those types of things. So we're really seeing now a throwback to how we did computing historically. So the role of our internet and our local area networks is becoming a bigger and bigger and bigger deal when we deal with our computers, and they're becoming smaller and smaller. Think about your smart TVs. For a long time, you had set-top boxes for giving you cable TV or whatever. Well, here I turn my TV on and I have, 50 different apps on it. I have HBO Max and Netflix and Amazon Prime, and these are all just streaming applications that are talking to something in the cloud, and I'm bringing all this content to my TV, and all I have hanging on my wall is a TV, and it's hooked to my internet connection. that's the state of our computing architecture today. And these things fall into this category. For us, we're focusing on the mobile computing architecture aspect of this. So as you start getting into the VR stuff and you look at, you know, some of the competitors. So for instance, I mentioned that I have a Pimax 8K downstairs. So that's what this guy is. This Pimax 8K. So it has 200 degrees of field of view. So I mean, it's almost like a human thing where the amount of stuff I can see at once is kind of, you know, pretty close to what a human being can see. Well, that's great. But the problem is this guy requires that I'm connected to a PC with a wire. All right. So while the visuals and stuff might be awesome, and maybe it's preferable to the Quest, it's not as convenient. I can throw the Quest on at any point in time, and within 30 seconds, I'm either playing you know, using an application local on the Quest, or I'm launching a PC VR application downstairs. Takes no time whatsoever. Way more time than it would take me to walk downstairs and get set up with this guy, and that also includes me navigating some stairs, which I don't like doing. So, you know, these are trade-offs when we talk about mobile versus PC VR specifically. So that's something you're going to be looking at when you talk about your Quest 2 versus Quest 1. Both of those guys, I have the picture up here. Both of these guys are, even though they're capable of doing PC VR, which is kind of like an extra awesome perk, they were originally designed to be solely standalone, completely mobile VR headsets. Everything you need is what you see here. Well, there's some hand controls, but they don't require any external sensors. They don't require being plugged into a computer. These are effectively smartphones that strap to your face. Okay, so that next assignment should be up. It's due on Tuesday. I put it up last class, so you should have had plenty of time to work on it in case some of you are going out of town or something like that for Easter. Questions, comments, concerns, bribes?
Isn't the PlayStation VR also kind of like another type of VR headset?
It is, but I would call that equivalent to like PC VR because it does require it to be tethered. So if you look at PSVR, and they're actually coming out with a PSVR 2. They haven't given us a release date yet, but this is what PlayStation VR looks like. You see there's this cable coming off the back of it. So that guy plugs into the PlayStation. So you have to be sitting there next to your PlayStation. And PSVR 2. So let's see if we got a picture of that guy. There's definitely renders of it. Oh yeah, this is a PSVR 2. Same thing. We have this cable. It's not out yet, but PlayStation VR 2 will also be a PC or a PlayStation required headset. It will not be wireless. It won't be standalone. So I wouldn't call it a mobile device. It's still going to be a cool VR device. Frankly, I don't know if it's that cool in my view, but I think it's a pretty substantial upgrade for PlayStation VR people, because their VR has been out for a long time. It has pretty antiquated controls and things like that, but it's still popular. I mean, it was a really, really well-defined, you know, really well-designed device. It just is a little bit old. Let's see if we, here's some interesting stuff here. So this is the, you know, PSVR 2, PSVR, Quest 2, and the Valve Index. Valve Index is probably our most popular PC only VR headset. You know, right off the bat, you can look at resolution of these guys. So PSVR 2 has basically 2K per eye. Quest 2 has almost 2K per eye. Valve Index has a little bit less. PSVR has a lot less. So I mean, this guy is much older. But you know, you can kind of look at the specs of these guys. What's nice in these new ones, and you'll read about this when you look at the Quest, is this idea of inside out tracking versus base stations. Base stations require that you have some stuff set up around your room that are looking at you, and they're tracking the headset and they're tracking your hand controls, as opposed to like the Quest uses inside out tracking. It had some cameras on it. If you saw, well, here's some examples. These have cameras for this is the PlayStation VR2, which is also going to be inside out tracking. So these cameras, they watch the hand controls and they see where your head's turning in the room and stuff like that. So you actually don't need external sensors. So anywhere you can move your PlayStation to, you can use your PlayStation VR2. Any place you can take a smartphone, any place you can move your Quest 2 to, you can do Quest based VR, which is kind of its secret sauce, if you will. All right, what else? Okay, well, I will see everybody on Tuesday.
See you.
Later.
Yeah.